We are studying metallic antiferromagnets. These are interesting as possible next-generation computing memory devices. And so we're interested in understanding the basic physics of how metallic antiferromagnets interact with current and with light.
The magnetic spins are arranged in ways where they are opposite each other. So if you could look at the spins on each atom, they're aligned up and down next to each other. And the goal is to have these magnetic spins turn in different directions. And so we want to be able to manipulate them.
We're looking at what happens when you take antiferromagnets and put large electrical currents through them or put magnetic fields in different directions, and can you switch the antiferromagnetic behavior that way?
Antiferromagnets have promise of scalability, so you can scale them to smaller and smaller sizes, and that means denser and denser circuits, and so more computational power.
The eventual goal is to use this sort of material in RAM, so random access memory in computers. They have some certain qualities about using an antiferromagnetic material in RAM, and that is it can be very fast and it's also very secure.
These antiferromagnetic materials are far less susceptible to external disturbances from the environment. So the memory that you store can be saved for longer periods of time.
We're using optical techniques and developing optical techniques to study the domains and the switching of metallic antiferromagnets.
We use lasers that produce very short pulses of light that are less than a trillionth of a second in duration. And by manipulating those pulses of light in various ways, we can probe the properties of materials.
We can calculate the various wavelengths at once, and then we can calculate the some kind of like a better wavelengths to detect this kind of the magnetology effect.
So our goal is to make crystals and materials where the spins are arranged in that particular way.
This is a big unknown, how you can switch it, whether it switches well. And so again, we do the electronic properties, but by combining that with ultra-fast spectroscopies and new materials that are being grown for us by collaborators, we can start to understand and maybe control these phenomena to hopefully use in the future.
I'm hoping that one day all the ferromagnets in the current storage devices would be replaced with my materials, the materials that I synthesize.
There's a need to develop new ways of thinking about how to store and process information, and my belief is materials are the key to that.